Chapter 2, Control Systems, Modeling in the Frequency Domain. So in this lecture, we're going to talk about the Laplace Transform, and hopefully you've seen some of this in your differential equations class. Of course, that class is more than likely approaching it from a very theoretical point of view, and we're going to avoid that. We're going to do our Laplace Transforms either using tables or using MATLAB. So let's talk about the Laplace Transform. So first, our objective is to introduce how Laplace transforms simplify many engineering problems. Uh, so the basic idea is that when you model a system, you can either solve it using differential equations, or you can use the Laplace transform to convert it to an algebraic expression and solve that. Typically, solving algebraic equations is much simpler than solving differential equations. This method is very efficient for solving control system problems and vibrations and circuit analysis, as we'll find. So the focus of this lecture is to be able to understand how to use the Laplace transform tables and to apply them to real-world engineering problems. So here's the basics. And again, if you took differential equations, they typically start by having you derive these, given a function that have you derive what the Laplace transform is. In this course, what we are going to do is we're going to typically use tables, or we'll use MATLAB. So here's a nice beginning table. Our book has a much more elaborate table, but these are the common functions you'll see. So the table has two columns. The left column is a particular function, and the right-hand side is the Laplace transform. So notice the function is a function of time, and the Laplace transform is a function of s. Typically, s is going to be the frequency. So if our function is 1, the Laplace transform is 1 over s. If the function is t to the n, our Laplace transform is n factorial over s to the n plus 1, and continuing down the list. So given a function, you simply look up what the Laplace transform is. It's sort of like looking up using an integral table, for example. There's some key properties of Laplace transforms. First of all, it's linear. So if you have the Laplace transform of a constant times a function plus another constant times a different function, you can break up the Laplace transform as follows, and this simply is similar to our rules of differentiation that you've seen before. There's another rule here that's kind of different. This is what's called a time shifting. If you want to, if you have a e to the at, where a is a constant times your function, the Laplace transform of that is simply given by the function times s minus a. So typically, you can look up in a table what the Laplace transform of f of t is, and if you have a e to the at multiplied by that function, you can just use that table to write the Laplace transform, substituting where you see s in the table, substitute s minus a, where a is the constant. There's also a differentiation property. So here, the Laplace transform of the derivative is simply s times the Laplace transform of the function minus f of 0, where f of 0 is the value of the function at time 0. Now, a lot of our problems, f of 0 will be 0. We'll assume that at time t equals 0, it's f is 0. So this part here typically will not be in our answer. There's also an integration property that you can see here. If you have an integral from 0 to t of f of tau d tau, then simply look up in the table what f of t is, and then you just divide that by s. So you can also go the other way. You can take what's known as the inverse Laplace transform. If you have f of s, you can convert back to the original function by again using a table. So here on the column on the left is a Laplace transform functions, and on the right is the associated function as a function of time. So for example, let's find the Laplace transform of the following function. So here, notice this function is a sum of different functions, so we're going to use the linearity property to break up the Laplace transform over each of these functions. And since this is a constant here, we can pull the constant outside uh, and write the Laplace transform of this function as a sum of Laplace transforms. Then we can simply use the table because e to the minus 5t, that's 1 over s minus a, where in this case a is minus 5. So the 6 gets carried along, and 1 over s minus a minus 5. Here we have a Laplace transform of e to the 3t, so in this case our a is 3. Now we have a t cubed, so we go down to this uh, column here. T to the n is n factorial over s to the n plus 1, so that would be 3 factorial over s to the 3 plus 1. The Laplace transform of 9 is simply 9 times 1 over s, because you can write this as 9 times 1. So it's 9 times the Laplace transform of 1, which is 1 over s. So putting all that together, the Laplace transform of this function is given by the following. We can also use MATLAB to find our answer. So you should go to the second floor lab or the first floor lab that has MATLAB installed, and you should run this script yourself and verify that the Laplace transform is exactly what we proved on the previous slide using the tables. And you can see here, this line here is what does the Laplace transform. Of course, you have to define the function, right? And this pretty f simply puts it in a nice, pretty format to look at. We can also use MATLAB to find the inverse Laplace transform. So let's say we have a function of s frequency given by the following equation. We can use MATLAB again to write that. So here, again, you should copy this code and verify for yourself. So here, the function I Laplace is what gives you the inverse Laplace transform. So here, this line is simply a repeat of what capital F is here. 6 over s, and then 1 over s minus 8, and then plus 4 over s minus 3. That's given by using this pretty capital F function. Simply spits out this line here. Then small f equals I Laplace big F. That's your Laplace transform right here. And I used this pretty small f function, which didn't really produce anything that much prettier than what the original version was. But you should run this code for yourself. So in the next example, we'll look at some examples of what's known as transfer functions and continue on. See you in the next lecture.